All right, today we're taking a look at section 2.6, more about rates of change, which is what we've been doing. But today we're going to do this from a graphing perspective. Okay, so everything's going to be graphs, and I don't mean graphs with your calculator. These are going to be interpretations of graphs that you're given, and then hand-drawn graphs that you create based on them. Okay, so if you want a straight edge, that's fine. I don't think you're going to need it on many of the problems, but there may be a couple places where you could use it. So to start with, our goal. Our goal is to begin with the graph of a function and then draw a graph that represents its slope at every point. Now, in the last section, you did this algebraically. They gave you f of x equals, you went through this limiting process, and at the end, on all of them, you got f prime equals another equation, right? But you did it with algebra. Agreed? We're going to do the same thing today, but we're going to do it based on the graphs themselves instead of the algebra component. So as we do these are sketches. They're approximations. We're looking for the general form of what it looks like, not very specific information. We won't have an f of x equals when we're done. But we're actually not going to start out with an f of x equals either, so it's okay. All right, so in general, what we're going to do, oh, why didn't you guys tell me it wasn't displaying? Oh, come on. Try again. How about this? You just have some words to fill in on the first step anyway. Graph of a function, draw the graph representing its slope at every point. Okay, so in general what we're going to do is we're going to look at a graph and we're going to list as many facts as possible about the slope. The slope. And then we're going to draw a slope graph for the curve. That's the general of what we're going to do. Specifically, we're going to look at the graph and we're going to state where the slope is 0. Definitely going to do that step. Sometimes it's never 0. We're definitely going to do that step. Step 2, we're going to state where the slope is positive and or negative. Definitely going to do step 2. And we're going to sometimes do step 3. Step 3 says to state how the slope changes. If you have a lot of information already from steps 1 and 2, you usually don't need to do step 3. Step 3 comes into play when you just don't have very much that you've been able to decipher from the graph from 1 and 2. You don't have a lot to go on. You have to go one step further is the idea. Okay, did everybody, oh, we still have people writing, sorry about that. Okay, does everybody have it all? We're good to go? All right. We're just going to jump right in and start them. We have a whole bunch of examples today. You're going to do a whole bunch more examples in group work. Today's just one of those example-only kind of days. Okay? There's no context and there's no calculators and there's very few places where we're going to see a number. It almost doesn't sound like math, right? Almost. Almost. All right. We have a graph. You guys know probably what the basic equation of this graph is. Does anybody know? It's cube. This is a cubic kind of graph. We've seen those back in chapter 1. And so we're going to talk about first, okay, well, you know what, let me do this first. Go ahead and write next to it, you need to split up your paper into 3 spots. So you're going to have, next to the graph, you're going to have another graph. And then over here on this side, if you will, you need space to write. Okay, so I'm kind of splitting my graph, or splitting my paper into 3 spots. The original graph, the graph I'm going to draw, and then the paper over here where I'm writing information. The axes where you sketch them needs to look somewhat like the axes you started with. So for instance, if you don't see a negative side of the graph on the left side of the graph, you're not going to need a left side of your graph either that you're drawing. Does that make sense? Okay. So you're just trying to get an approximate of what it was to begin with. All right, so our first step is to write down places where the slope is 0. Okay, so where is the slope 0? So I want you to actually write down this word, slope is 0 at. The more language that you write down with these, because we're going to do a couple steps inside of this language, the easier it's going to be to draw your graph when we're done. So the slope is 0 at. Where is the slope 0 on that graph? A. Uh-huh. At, you know what, that's a good place to say it, actually. X equals A and X equals B. If you just want to say at A and B, that's fine. And that's it. Step 1 done. Step 2 is to list the locations where the slope is either positive or negative. Now here's the catch. Over here on this graph, the slope is positive when the graph is doing what? Increasing. So all the locations on this graph where you see the graph increasing are places that if you were to draw the tangent line in those spots, and over here as well, you would get a positive slope on your tangent line, right? This tangent line would be going uphill. So when we write this down, we want to use the phrases positive and negative. We do not want to use the phrases increasing and decreasing. It's the graph that's increasing and decreasing, but it's the slope that's positive or negative. And there is a difference, and it's really substantial later on, okay? Positive and negative. So the slope is positive from negative infinity to A and from B to infinity. So far, so good. That's the positives. And then we want to write down that the slope is negative. Where? From A to B. And that's enough. We don't have to do step 3 on this problem. Okay? So we're going to start with the step 1 and 2 so that you can see what's going to happen and why you'll see very quickly why we didn't need to do step 3. Okay, so here's what I want you to do. Grab some other pen or pencil that you have in your bag that is not the same color of what you're using right now. So maybe you have, it could be a crayon or a highlighter. I just need you to grab something that looks different than what you're using right now. If you don't, grab somebody from a neighbor. I may even have some purple grading pens with me. I do. Does anybody need a purple pen? Here? Okay. Okay. Do you guys have something over here? Everybody good? Okay. Are you guys ready? Yes. Awesome. Okay. What I want you to do is everywhere you wrote the word slope, I want you to mark it out. So there's 3 places we wrote it. Mark out the word slope. And right on top of where it is, I want you to write down y value. Y value and y value. We wrote down a whole bunch of information about the slopes. And now we need to create a graph whose y value does those things. So when I go back to read what I wrote, I want to read y value in the place of slope. So for the first one, it says now the y value is 0 at A and B. What does it look like for a y value to be 0? It's on the x-axis. So you need to make sure A and B are in roughly the same location that they started out in. Don't go moving them around. So here's A, here's B, roughly. And you need to draw a y value at A and B, which is an intercept of the x-axis. That's y value A and B equal to 0, or y value equal to 0 at A and B. Okay, that's sort of like step 1 done. Step 2 says the y value is positive from negative infinity to A. So before we get to A, the left-hand side over here, the y value is positive. Where on a graph is a y value positive? Anywhere above the x-axis. So I'm going to draw my graph above the x-axis. And I want you to notice that I crossed the y-axis. And the reason I did is because the original graph did too. Okay, the original graph is on the left-hand side of the y-axis, so my graph needs to be there as well. Don't go putting like asymptotes in that don't really exist. Okay, they really do go on this side of the graph. What in the world does it say happens between, I'm shifting mine because it looks sloppy. What does it say happens between A and B? Y value is negative. What does it look like for a y value to be negative? It's beneath the x-axis, right? It's lower on the graph. But it still has to connect the 2 points that are already there. So I have to connect to this point and to this point, where I've got the circles in yellow. I have to connect them, but I have to connect them and be lower than the graph. So there's really only one thing I can do. I have to start at one, I have to end at the other, and I have to be beneath the graph. That's what I get. And then what does it say happens from B to infinity? The slope is positive, right? So if the slope is positive, that means my y value now is positive. So my y value is positive, and y value being positive is above the x-axis. So I finish off the graph, much like I started it, with this image. If this graph were identified for us as f of x, what we just found would be identified as f prime of x. And of course, it is a sketch. And in fact, you'll notice there's not even any, especially on the y-axis, any units or indication of how far, how spread out, or how compact this is. But the basic shape should all look, for everybody's, like a parabola. And that's what we get. Are we good with that? Do you guys have a question? No? Okay, just checking. Okay, you ready for another one? Excellent. Now we are going to start with a parabola, right? So let's sketch our graphs, for our axes for our graph. And we should probably go ahead and mark out A on here. That'd be fine. Here's A. And it wouldn't be a bad idea to notice that this graph is actually completely on the right-hand side, isn't it? There's nothing on the left-hand side. So when I sketch this in a moment, I don't know for sure that it crosses. If it's a parabola, will it eventually cross that axis? Yeah, it will. So just keeping that in mind. But all right, so let's take a look then at what we can write down for this one. Our first step is to list where the slope is 0. So where is this slope 0? Right at A. It's 0 at A. Now what can you tell me about positive and negative in terms of this graph? Where is the slope positive? Right, the slope is positive from A to infinity. And then how about the slope being negative? Yeah, negative infinity to A. So we anticipate that it does in fact continue on past the y-axis just because of the general shape we're given to begin with. Okay, everybody good so far? Okay, I really can't make a lot of comment on step 3 on this one, and this is pretty much enough to give us a good idea of what's going on. So if we take a look at this one, we're going to now change all my slopes into what? Y value. So mark them out with a different color and write in Y value. Okay, step 1, I need a Y value that's 0 at A. What does that look like? An x-intercept, exactly. So I need an x-intercept at A, like this. Now what's happening before A? If we read our graph from left to right, the stuff before A, what is the Y value? Negative. It's negative. Our Y value is negative before this. Is it? Yes, Y value is negative. Sorry. Something weird's going on in my paper, but you're right. The Y value is negative. So what does it look like for a Y value to be negative before this point?
Below the x-axis.
Below the x-axis. So at the very least, we know that it's down here somewhere. I'm just going to kind of leave it funny like that for a second, and I'm going to show you 2 options on how you could finish it out. Okay? And then what happens after A on the right-hand side from A to infinity?
Increase. Or positive.
Positive. The slope is positive, so our Y value will be positive. So our Y value is positive over here. Okay, so here's a couple of ways you could draw this. This might actually be a line. Totally a possibility with that piece of information, right? Yeah, it could do that. Another option is it might not be a line, it might do something where it curves a little bit somehow. We don't have anything to actually help us know which one it does. And the reason is because we don't know what this curve is. If this curve is in fact x squared, this is in fact going to be a line. But if the curve is something like x to the 4th or x to the 6th, which look a lot like x squared, it's going to look more like this curved shape that I drew here at the end. Okay? Either one's acceptable at this point because we don't have any more information to be able to use to determine it. Okay? So I'm going to leave mine on this because I've already got it on here right now. All right, let's take a look at C. No question now, this is in fact a line, yes? Definitely a line. So let's sketch for our next part, the axes. And this one is a fun one to write out. Tell me what you know about the slope and where it's 0. Nope. Good try. Where is the slope 0? Never. This slope is never 0. If I draw a tangent line to this curve, what's it going to look like? The line itself. Every tangent line is going to look like the graph itself on here, isn't it? So this slope is never negative. Never 0, so I'm going to say never 0. There we go. Never 0. All right, how about positive versus negative? What is the slope? It's positive. And where is it positive? Yeah, so slope is positive. You can either say from negative infinity to infinity. You could actually say the word everywhere, or that it is always positive. Any of those would be fine. This graph's slope is always positive. Now we get to actually do a step 3. It is always a positive slope. But there's something else about this that's different than the last 2 problems we did. What can you tell me about this slope? The origin's the x-axis, but that's not related to the slope. That's related to an intercept.
Changes quadrants.
No, I mean it does, but that's not related to the slope either. Constant. Oh, it doesn't change. You guys, there we go. Okay, that's the one we want. So we're going to write down that the slope, you can use the phrase is constant. You can say that the slope never changes. Whatever phrase of that you like, it's the same thing. And that's how the slope is changing. In fact, it is not changing here, right? The slope on this never changes. So everywhere I have slope, what am I going to do?
Y value.
Y value. That's right. We're going to write Y value, Y value, Y value. Now, what does it mean to have a Y value that's never 0? What does that tell you?
There's an asymptote at
Nope, there's not an asymptote.
just never. Do you know what x-axis?
It never hits the x-axis. Yeah, it never equals 0, and equaling 0 is the equivalent to hitting the x-axis. This graph will not cross the x-axis. Everybody good with that? Because the x-axis would have been a location where the original graph slope was 0, and we didn't have any of that. So we're never going to cross the x-axis, which means we're either going to be contained entirely above or entirely below. Which one is it going to be? Above. Why is it going to be above, Braden? The slope is positive. And if the slope is positive, then our Y value being positive means it's going to be above the x-axis. Not only do we have a graph that is entirely above the y-axis, what else do we know about the Y values? It's constant. What does a constant Y value graph look like? A line, but what kind of line? Horizontal. This is going to be a horizontal line. Because on a horizontal line, you have a constant Y value. And it's positive from the original information as well, and it never crossed the x-axis. Now, I want to show you that just because the graph has some of these features doesn't mean it has the same ones to every graph. So this graph will start out feeling much like the last one, but clearly this is not a line, right? Right, definitely not a line. Okay, so let's draw our axes, and let's write out our facts. The first facts about slope being 0. What can you tell me about the slope here and being 0?
It gets closer to 0 as it approaches negative.
Yeah, so it never actually equals 0, but it gets really close to 0. So that's actually useful information to write down. We understand it's not actually 0, but it's going to help us with our graph if we write down what we do see. So we're going to say that the slope, I'm going to use the phrase is almost, or you could say is approaching, is almost 0 as x approaches negative infinity. That's how I write it. As you go to the left, far to the left forever, the graph gets really, really close to a slope of 0. Agreed? Okay. What can you tell me about positives and negatives in the slope?
It's always positive.
It's always positive. Now, that's just like my last graph. The slope is always positive. That step is like my last one. And then step 3 is how is the slope changing? So we already said on the far left it's almost 0. We could have included that in this part right here. It's almost 0. What's happening as the graph continues toward the right? It increases, it gets more vertical, and it does it rapidly, right? It's getting steeper really fast. So we could actually use the phrase that the slope is, and I'm going to say is getting more positive because I really don't want you guys to start using the words increasing and decreasing in the wrong place, so I'm just going to avoid them altogether. The slope is getting more positive. We don't want to say that the slope is getting steeper because it's not the slope that's getting steeper. The graph is getting steeper, and we care about the slope. The slope is getting more positive as x approaches, and this is a positive infinity as opposed to a negative infinity. Okay, let's change all of our slopes to y value. And we're going to do the graph from left to right. We don't have any intercepts, right? There's no places where it crosses the x-axis. And this graph is lying entirely above, just like the last one did. On the left-hand side, it tells us that the slope is what? It's positive, and it's almost 0. So we need a y value now, a y value that is almost 0, but positive on the left-hand side of the graph. So it's going to look something like this, right? Those are y values that are positive, but they're almost 0. They're almost hitting the x-axis, but they're not quite there. They are above. And then it tells us that the entire slopes are above, right? The entire y values are above. So as I move to the right, what is happening to my y value according to step 3 on this? Yeah, so as we move across the graph horizontally, the graph gets vertically bigger, right? It gets more and more and more positive. Well, I think I described that, right? That's a little weird. Why is this a little weird? Some of you are looking at me like I'm crazy. It's the same graph. And we will encounter the function that actually does that. This is the only one that does, where its shape of its original graph and its shape of its derivative graph are the same shape. They may not be exactly the same values. One of them may actually be steeper or shallower, but the shapes remain the same because the slope and the y values are doing the same thing at each location, which is unique. Doesn't happen very often. Now, there are some places where rates of change, instantaneous rates of change, or slopes do not exist. There are 3 locations. Okay? The first location is at discontinuities. I'm going to draw you pictures once I get them all on the screen. Discontinuities. The second is at sharp points. So quick changes in direction. Sharp points. This is also sometimes called cusps. C-U-S-P-S. And then the last one is when the tangent line is vertical. Okay, so we will not have a slope at a discontinuity. So if the graph does this location where there's this jump in the graph, or even if there was a hole in the graph, it would be a problem. This location where there's a jump in the graph is discontinuity. That location has no slope. It doesn't exist. So the instantaneous rate of change, the derivative, all those words we've used for the same thing, they don't exist there. Sharp points. If the graph is continuous, but it has this sort of quick change in direction, it's got a corner on the graph, it's got a cusp in the graph, a fold or a bend like this, where it's not smooth, the derivative does not exist there. The slope does not exist there. And if you can imagine drawing tangent lines, especially on this one, you can convince yourself that that makes sense very quickly. What in the world would be the tangent line where it would look like it's really, really close to the graph on both sides? It's weird, right? Because it changes direction so quickly. And the last one we do not see happen very often. It's the rare occasion kind of thing, and I don't know that we'll ever see it, but it is a true statement. If the graph had a location where right in here the tangent line was vertical. I can't even draw it, it's so awkward. Something like that. Got a tangent line that's vertical. The tangent line exists. That's totally fine. But what is the slope of a vertical line? It doesn't exist. There's a word we often have used for it. Do you remember it? Undefined is the word you've seen before. So since the slope is undefined, that is, there's no numerical value to relate to it, that value, which doesn't exist, means that our slope doesn't exist. Okay? So the instantaneous rate of change, the derivative, they don't exist at those points. These are our three locations where the slope fails to exist. And so now we get a much more fun graph than we had previously. Don't you think it's much more fun? No? Come on. What fun are you guys? Okay, here's what you're going to do. You're going to draw yourself an XY axis and make the hash marks in there that the original graph has. So the graph has something like, and it doesn't have to be super precise, but it should be reasonable. 2 hash marks on the left. I've got, I think, 5 on the right. There are 2 or 3 below. I think it should be 3, but I couldn't get all of them to show up on my graph correctly. And then 4 above when I was moving it into PowerPoint. Okay, the directions tell us a little bit different, or give us a little bit different information than the last set. It says indicate the input values for which the graph has no derivative. So we will do that and explain why. And then we're going to have to draw the derivative graph. So let's go ahead and indicate the values for which it has no derivative, and then I will work with you to explain why, but I won't write it on my screen because this is the only slide I've got at this point. I should have had an extra blank slide and I forgot. Okay, where does the derivative not exist on this graph? At what x values? Okay, so at x equal 3 and 4, is that it? There's one more. X equals 0. Okay, let's start with 3 and 4 because those are the first 2 that you guys noticed. What's going on at 3 and 4? There's a jump in the graph. The graph jumps from a closed circle to an open circle in those locations. It's a discontinuity. Okay, so there's a discontinuity at 3, discontinuity at 4. We will not have a slope value there. What's happening at 0? Yep. Do you know what we call that, Luke? Okay. Does anybody else remember what we call it when we're approaching the line there and this doesn't actually equal it? Asymptote. Yeah. there's an asymptote on the y-axis. It's a discontinuity, it's just a different kind of discontinuity, right? We have a discontinuity at x equals 0. So in some sense, all three of these locations are because of the discontinuity fact of the last set of three examples that I gave you. Three reasons for being not having a slope. They're all discontinuous there, but they're discontinuous kind of in different ways. Now here's the catch. When it's discontinuous with an asymptote, your derivative graph, the slope graph that we're drawing, will also have an asymptote there. We are going to get an asymptote still right at the x-axis or the y-axis. It's going to be there. So, and you'll see it happen as we write the facts out why it has to work that way. So bear with me on that. It also has to do with, do you remember when I told you when we were looking at the last ones, if the graph crosses the x-axis, your graph will too? Remember I said that, or not the x-axis, the y-axis. If the graph is on the left side and the right side, then your graph will be too. Same thing here. This graph is not at a y value, an x value of 0. So your graph won't either. Okay? So the discontinuity is happening at 0, 3, and 4. Let's write down some facts. Where is this slope 0? Three to four. So right here, this little spot, and 4 to 5. It's flat, right? If you drew tangent lines there, they'd be horizontal tangent lines. Agreed? Yeah, so the slope is 0 at, or maybe on, since we have an interval, on the interval from 3 to 4 and the interval from 4 to 5. Why can't I write 3 to 5? Because there's a jump at 4, right? So I have to have, there will be a way that I draw that, and I'll show you, but there will be a way that I draw that is not smooth and easy, nice and pretty. It won't connect. All right, that's my slope being 0. How about the slope being positive and negative? My suggestion is let's start from the left-hand side of the graph and write things down as we move from left to right on this one, because it's a little more complicated than the other ones. What can you tell me about the slope of the graph over here? It's negative. Okay, but you know what else is going on here? What can you tell me is happening on this edge? Yeah, it's almost 0, right? I almost feel like we should include that either in step 1 or step 3. We'll wait and do it in step 3 this time since I've already written step 1, but we will have that to include. But the slope is negative from negative infinity, oops, let me do it down here, to 0. Right? This is a negative slope. Okay, then I've got an asymptote, which we talked about that. What's going on in this piece right here? What's the slope? Negative. It's more negative. It looks different than the first one, but it also is negative. If you draw a tangent line, it is going to be a line that has a negative slope. So again, the slope is negative from 0 to 3. And then we already wrote down what was happening from 3 to 4 and 4 to 5. So we don't need those two pieces. It will help us, especially on the first two pieces, because we don't have that much information if we can cite what's happening. So I think Alex was the one who said that on the far left, no, it wasn't Alex. Was it you, Kendra? Yeah, okay. On the far left, it's almost 0, right? Or approaching 0. It's nearly 0. This portion of the graph over here flattens out, doesn't it? I mean, compared to the rest of it, it's lots flatter. So the slope is nearly 0. Whoops. So I'm going to say that the slope approaches zero as x approaches negative infinity. As we go to the left, and you don't have to use the arrows and use the words approaches, you can write it left and right, that's fine, it doesn't hurt anything. You're not going to be super much graded on these words being exactly like mine. You do need to have positives and negatives and not increases and decreases. But write it in a way that when you read it, you know what it's describing so that you'll be able to use it. Okay? Where else is the slope changing, or how is the slope changing on that first piece? What happens, like on the far left, on this part of the graph, it's going to be 0. What's happening as we get closer and closer to the y-axis? Yeah, like it is super negative, right? Those tangent lines almost become vertical, don't they? If this graph continues down and we indicate it looks like it does, those tangent lines are nearly vertical tangent lines. The slope is so steep and so negative. So we can write that down. So the slope is very negative, or it's, approaching negative infinity if you want. So the approach is very negative as x approaches 0 from the left. There's that fun limit notation that we had seen before. 0 from the left. Or use the words, as you get close to the y-axis on the left side. Use it, that's fine. You can do that. All right, our other piece right here, what can you say as you're close to the y-axis on the right-hand side? Is it very positive? Careful. Remember, we're talking about the slope, not the y-value. The y-value is very positive. What's the slope? It's also very negative, just like the other piece was. It's very negative, but it's at a positive y-value doing it. Again, think about drawing the tangent lines. These tangent lines are very steep, and they're very downhill, right? Very, very steep and negative. So the slope is also very negative. As x approaches 0 from the right. The right-hand side of 0, but close. And then what happens as we move along the graph toward, trying to collect it all to move this, make it a little bit smaller. Hang on just a second. What happens as we move along the graph? All right, let's just do that first. Towards x equal 3. As we move along the graph this direction, this piece. Is it still negative, the slope? It is. But it's flattening out too, correct? It's leveling out to being about what? About 0, isn't it? So the slope's almost 0. So again, much like the last phrase, we can say that the slope approaches 0. Still didn't get it big enough, small enough to give myself space. There we go. That's what I wanted to do. So the slope approaches 0, or becomes nearly 0, something like that, approaches 0 as x approaches 3 from the left. That's the yellow part that I just circled right here. Okay, you ready to draw that onto a graph now? We had a ton of pieces of information. Let's start with the easy pieces. The horizontal flat ones. Can we do those first? Okay, what was this? Oh, we need to change all of our things to y values. Let me do that first, actually. So we've got y value, all the way down. Okay, they're all y values. I need to have a y value that is 0 from 3 to 4 and 4 to 5. What does it look like to have a y value that's 0 from 3 to 4? Where's it going to be? Okay, so what does that look like, though? Can you describe it in like a picture form of words? Where is it? On the x-axis. I will be on the x-axis from 3 to 4 and from 4 to 5. So I'm going to draw this with the yellow so I can see it better. All right, so here's 3 and here's 5. So from 3 to 4 and from 4 to 5, I'm on the x-axis. But I'm not really supposed to be on the x-axis at the 3 or at the 5, right? The graph's derivative doesn't exist there. So I make big old open holes there. Hard to see, but hopefully yours will be better. There are open holes in the graph. The derivative does not exist in those locations. Now let's look at the far left-hand side. The graph is supposed to be negative because it says the y value is negative. It also tells us that the y value is nearly 0 on the left, and as we approach 0 itself, the x value of 0, it becomes very, very negative. So the slope is nearly 0, and then it's approaching a very negative value. It looks the same, right? It looks the same. But the catch is that the next piece, although it has a similar shape, right? It's got the same curving shape on this second piece that the first one does. It's not going to look the same as it started. Because when it started above the y-axis. Why is it now going to be below? What do I know about the slopes of that part of the graph? Their slopes are negative, right? The slopes of this portion of my graph are negative. So if the slopes are negative, my graph that I'm drawing now will have negative y values. So the negative y values mean I'm going to be beneath the graph. And it says that as x is approaching 0, that means parts of the graph that are near the y-axis around here, the graph is very, very negative sloped, which means it's going to look like this. And as the graph approaches 3, the slopes approach 0. They get really close. So the graph becomes something like this. There might be a jump here. There might not be. It could actually connect those two open graph holes. They would still have an open hole, but it could actually connect together, like the open hole could be the same. Slope is negative. It's very, very negative near the y-axis, and it's becoming almost 0 near x equal to 3. Any questions on that one? I think you only have like one of those for your homework or something, so most of them are of the variety like these were over here. Okay?